start. Welcome back, everyone. So last time we went ahead and we covered MOSFETs, specifically that enhancement type MOSFET power that we were using for switching some load on and off. So something like a motor. This is very typical of an application of using a MOSFET. You would use some type of digital device like a microcontroller, FPGA, some digital logic, something that we want to control the current that's flowing through our load. In this example, I'm just using a motor, and so we would want to turn this on and off. And what I want to cover today, we calculated this last time. What I want to cover today is a couple of practicalities of using a MOSFET in this example, and then we'll build upon that. So one of the first things I want to draw your attention to is when you have a MOSFET in an application like this, you're controlling the gate with a digital logic signal, 0 volts or 5 volts. You're turning this guy on and off, essentially. Now, the benefit of a MOSFET as opposed to a BJT is less current going into the device, right? So as far as driving this from a logic signal, you can count on a very high impedance. So we can be guaranteed that we will not use very much current going into the device. That cannot be said for a BJT in a similar type switching application, because a BJT is going to use quite a bit more base current compared to the gate current that would be going into this device. And the reason for that is inherent in the construction. When you construct a MOSFET like this, we have a conductor, we have an insulator between the gate, the conductor on the gate, and the conductor of the body of the MOSFET. So the body of the MOSFET, which is constructed out of N-type material and P-type material, is also conductive. Granted, it's a bit less conductive than the actual gate is, but nevertheless, we have a conductor here, we have a conductor here, and we have an insulator between those two. So what we have formed between the gate and the body of this MOSFET is what? What happens anytime we have a conductor and another conductor separated by a insulator? We get a capacitor. So, in other words, we get some gate capacitance. Now, this gate capacitance is what's responsible for giving us that desirable, very high impedance input into the device. However, it does create a little bit of something that we should be concerned with. Now, when a capacitor has no charge on it, and you initially apply a voltage to it, how much current does this draw? Well, when a cap has no charge on it and then all of a sudden we apply a voltage to that gate or to a capacitor, turns out it's going to draw a lot of current. Have you guys ever noticed you wake up in the morning, you go to plug your laptop charger in or any device, it's been sitting all night, so the caps have lost any charge that they had built up on their plates, and you go ahead and plug it into the wall. You ever see a spark that comes out of it? when you initially plug in some appliance into your electrical outlet, yeah, you'll notice you see some sparks come out of the outlet. The reason for that is that that cap is drawing a lot of current at time 0. Before that cap builds any charge on it, it acts like a short circuit for that brief moment in time. For that fraction of a second, it draws a lot of current. Now, you can actually see this if you go ahead and remember the universal time constant chart for an RC circuit from 211. If we have an RC circuit over here, and you go ahead and graph that percentage of max value, to the time constant. Now for this simple example, the time constant is RC. Well, the voltage that develops across this capacitor, in other words, VC, looks something like this. However, the current going through this capacitor starts off at 100%. Okay, whatever that max value is. Now over here, the max value of our current being going through this capacitor would be determined by the voltage applied divided by R. So if we went ahead and called this V in, then this would be equal to V in divided by R. But let's go ahead and draw up a typical example of using this cap. Sorry, not using this cap, using this Mosfet. We have this gate capacitance formed here. What's R? R is like 0 ohms over here. If you imagine a little bit of resistance here, if I just go ahead and connect the output pin from some microcontroller to the input of my MOSFET, yeah, I have 0 ohms right there. So if you imagine that I have this capacitor that's been formed here between the gate and my current going in there, well, now look at what happens. My R is 0. And so with my R being 0, we can expect that our current is a very high value at time 0. Okay, so that's a problem because notice this is going to go to infinite. Obviously, my microcontroller cannot supply infinite current, but nevertheless, it's going to be as much current as is possible at time 0 to turn on this MOSFET, okay? So we don't like that situation. That's stressing out the microcontroller. That's leading to a lot of current dumping into this input of this MOSFET very quickly. But this would cause some damage, stress out the output circuitry of this pin of my microcontroller or my FPGA, whatever it is. And so we want to go ahead and fix that. We want to address that little practical problem that we have with using a MOSFET, which is we want to limit the inrush current of the MOSFET. So let's go ahead and let's fix this. Let's just put some resistance over here, 4.7K, 1K, 470 ohms, all are valid. Kind of depends on your situation you're in, but let's go ahead and say 470 or 1K or 4.7K. We just need something here. And now we have some mechanism to limit the inrush current. So let me go ahead and write that. Okay, so generally good practice to do this. Okay, now another side effect of having this gate capacitance on this MOSFET, and obviously this gate capacitance is a very desirable thing from the perspective of the MOSFET being on, because it means we're going to use a lot less current to keep the MOSFET on, but it does create this situation where we should put some resistance in there to limit the inrush current. But another side effect is that capacitor, when you charge a capacitor and then I pull that capacitor away, that capacitor is going to remain on. Okay, so what this means and I'm using the abbreviated schematic symbol for this for these MOSFET circuits. They're the same as this. I'm just drawing it because this is much quicker for me to draw. Okay, so another side effect of this is if I apply 5 volts over here and then I build up the charge, on this capacitor, and then all of a sudden for some reason we disconnect. So we lose the connection to the microcontroller, or there's also situations where, depending on the configuration of these digital logic pins, you may not have a strong path to ground in order to discharge. So we're talking about going from on to off of this MOSFET. It would be nice if we had some fail safe so that if this circuit disconnects for any reason, that we safely put this MOSFET back into an off state, because generally speaking, if we lose a connection here, we would like the whole system to default to a safe situation. And then on top of that, depending on the circuitry that's inside of the microcontroller, maybe you don't have a strong pull down network inside for some reason, then we would be well served by also putting a resistor from this input down to ground in order to give us another path to discharge. Okay, so to leave this in a safe state in case something happens over here, or another good reason, maybe when your FPGA first starts up, when you initially power on your FPGA or your microcontroller, maybe those pins are not configured to the best configuration, and so for safety reasons, pretty good idea to do this. Put in something like a 200k ohm resistor. We're not talking about a very low resistance, we're just a very large resistance to help us discharge the capacitance on this MOSFET on the gate. So we have this guy here. Limit the inrush current, and then another one over here in order to discharge the gate capacitance in case anything else happens over here. Okay, so these are very good practices to use when using a MOSFET. Okay, that makes sense? Cool. All right, let's go ahead and let's bring in one more issue. Now, this last one, this is a function of the type of the load that's going to be that the MOSFET is controlling the current through. So let's go ahead, let's give ourselves a typical setup. Okay, so this motor is obviously a resistance. It is acting like some type of load. It's got some resistance. The motor is the one that's limiting the current through this, and we want to turn the motor on and off. This is a very typical switching circuit that you would encounter in 346, 347, 447, or in the future. There's many things are going to look like this, so it is a good example. However, is this motor just a resistor, or does it also look like some other property that we're familiar with? How do you construct a motor? You wind a lot of wire around something, right? You create an electromagnet. So that's my hint right there, is you have a lot of wire coiled around something. What is that property? Inductance. Ah, it's an inductor. Yes. I guess load inductance? Sure, I'll run with it. Okay, so this motor is not only a resistor, it does have a lot of this property called inductance. Okay, what does that mean for us? Well, when we take an inductor and when we pass a current through it, we get an expanding magnetic field. Okay, so we get this expanding magnetic field inside of this inductor. That expanding magnetic field induces a voltage in the opposite direction of the current that caused it. So this inductor will, when we have current going through it, in other words, when we turn it on, when we go from zero current to some current, we get this expanding magnetic field, and it will induce a voltage like this. Now, this isn't a problem. Going from off to on is not a problem. However, when you go from on to off, you're going to get a collapsing magnetic field. Now, when we get a collapsing magnetic field, it's because we went from a situation that had more current going through it, and now we're going to a situation where we had much less current going through it. In other words, we switched the MOSFET off, but we had current flowing through this. That's exactly what happens when we turn this MOSFET off. And so this motor gets a collapsing magnetic field. That collapsing magnetic field induces a voltage opposite of the change that initially created it. So we end up with an induced voltage in this direction. Okay? Let me go ahead and draw this in. If we're all comfortable with this idea that this collapsing magnetic field creates this induced voltage inside of the motor, in the inductance of the motor, or the inductance of any load that we have here, it's going to behave like this for a period of time. Well, what happens when we go from on to off? No. The motor won't run backwards because the motor's still going to be, the current is just decreasing. the collapsing magnetic field of that inductance is not going to cause the motor to turn. What will happen, however, is that you will get an induced voltage that behaves like this, where if this is 5 volts, you now have a voltage at this point which is much higher than 5 volts. If I take the minus side of a battery and plug that to 5 volts, whatever I have on the other side is much larger than 5 volts. Now, you kind of need to talk about what's the magnitude of the induced voltage when the magnetic field collapses of this inductor. Now, that's given by Faraday's law. You don't need to know it, you don't need to calculate it, but you do need to know that the result of Faraday's law is that this voltage can actually be quite large. In a typical application, you can be expecting 100 volts of back EMF. 100 volts of back EMF or counter EMF or whatever you call that induced voltage from the collapsing magnetic field of this inductor. So what's the voltage at this point? 105 volts, right? It's whatever the induced voltage is plus 5 volts. So for this quick period of time, you get this voltage spike coming from this inductor. And if you want to, I could show it on an oscilloscope and hook up an example here if you wanted to see that what this induced voltage spike looks like. It is quite large. It's actually quite frightening how large of a voltage spike that you will get from a collapsing magnetic field from an inductor. Now, to give you a heads up, modern day power supplies, they call them switching power supplies because they are switching an inductor on and off. So for a power supply application, this actually is desirable because it lets me create voltages that are much larger than my input voltages, because the collapsing magnet, there's no limit to how high this voltage is of a collapsing magnetic field of this inductor. You're just what limits it is the resistance of this inductor, the practical considerations, what we generally regard as the parasitic properties of a component. If I had a pure inductor, it would have 0 resistance, but I can't have a coil of wire that has 0 resistance, so it has some resistance. Those are referred to as parasitic properties. But that's okay. Let's not go down that rabbit hole. What's important here is we get this 105 volts. Will it damage the motor? No, because your motor is just a coil of wire, and a coil of wire, generally speaking, does not care if you have 100 volts going through it for a fraction in time. What does care about this 105 volts is this Mosfet. Okay, this Mosfet will definitely get damaged during that transition from on to off because of this induced voltage. So there is a way to fix this. I don't just like to describe problems, I like to give solutions to them too. If you notice, the voltage here at this point is higher than this point. So what if we just slap in a diode in here? Okay, under normal conditions, this is higher than this point. It should be. If we're running this and we're turning this motor on and off, on and off, on and off, this voltage at this point should be higher than this all the time. Higher voltage over here, lower voltage over here. Diode's not conducting, okay, during normal operation. But when we have the case of having 105 volts over here, notice what happens in this example. Okay, now whenever the induced voltage spikes unwantedly in this direction and we get 105 volts at this point, now this side is higher than this side. That means this diode is going to conduct. Okay, and it's going to allow the induced voltage from this collapsing magnetic field to safely discharge into the positive side of our voltage source. Now, this is very common to do, and there's a name for this. We call this a flyback diode. In fact, let me go ahead and just to validate myself a little bit here. If I just type in the word flyback diode, I was looking for one with a motor. Oh, here we go. You'll see this commonly done anytime you have an inductive load, which is a motor. And so over here you can see just this image that came up from SparkFun. Okay, so they added R1 to limit the inrush current. Well, actually in this case they're using a BJT, so R1 is not limiting the inrush current, but it is limiting the base current going into this BJT that's being used as a switch. But you can see over here the flyback diode is placed in parallel with the inductive load so that when the magnetic field collapses and that voltage spike is induced, there's a pathway back to 5 volts in order to suppress that voltage spike. But you'll see here, here's another example. Here's one that's being used. Again, it's this essentially the same thing. They just have a changing voltage. So instead of having a Mosfet to change the applied voltage, they have a voltage source. And so they're modeling whatever the load is as a series L and R circuit. And then here's the flyback diode that's been placed in parallel with the load. Yeah, this is just a thing to do. It's a good thing to do. And sometimes it's a necessary thing to do because you can definitely damage the MOSFET and you can damage the microcontroller. If you damage this MOSFET to the point to where this 105 volt spike actually makes its way back into the device, you can cause a lot of damage on these pins over here. A lot of our sensitive digital circuitry does not play well with large voltage spikes like that. So you need to be cautious anytime you're switching on and off an inductive load. Okay, so let me go ahead, draw, and put all of this together. So everything we've talked about thus far for a very common application that you would do when you're making a little robot project in 346 or 347. You're going to be using some microcontroller. You're going to put some resistor to limit the inrush current. You're going to put another resistor over here in order to safely discharge the MOSFET. And you're going to put some flyback diode in here to suppress that induced voltage from the inductive load. Maybe something like 470 ohms there and 200K here. Someone's about to ask what kind of a diode works well for this application. A 1N4001, 1N4002. Those silicon rectifier diodes can work pretty well as a flyback diode. So this is kind of the entire switching circuit to turn our motor on and off. Okay. Now you may also be asking, well, I said this was pretty good. Is there better? Yes. Schottky diodes work great in this application. So let me go ahead and say, or, so that you don't get the idea that a 1N4002 is a Schottky diode. What is a Schottky diode? A Schottky diode is another type of diode that actually can switch on and off much faster than a rectifier diode can. Rectifier diodes are great for very large voltages. They're good for large currents. That's why we prefer them for constructing linear power supplies like your full wave bridge rectifiers. But that being said, they don't switch as quickly as a Schottky diode do. Schottky diodes can switch very fast. We're talking maybe an order or two magnitude better. So a Schottky diode generally can switch 30, 40, 60 picoseconds, where a 1N4002 is going to be a bit slower than that. And switching quickly, so changing from conduction to not conduction is what I'm talking about when I say a diode switches. From going from reverse bias to forward bias, that switching action, Schottky diodes can do it much quicker. Yeah. Okay, and there are, you can do a Google search for like some jelly bean Schottky diodes. What are some of the #5819 is a general purpose. 1N58. That's a good general purpose Schottky diode if you're interested. The question was, sorry, what was that?
When it comes to handling flyback, are diodes always used, or are there any other alternatives?
Oh, that's a good question.
Because I'm assuming like if you just get a really large motor, then you can't just slap a diode on it.
Sure, why not? That's a good question. What other mechanism for doing a flyback function? I'll be honest. I've never actually seen something else used to do flyback. I'm wondering, you could probably get away with using another type of MOSFET circuit in that application, but I don't know off the top of my head. That's a good question. I don't have an answer. I don't have an answer for you. I will say every flyback situation where you're doing this, I've always seen a diode used. And the thing is, I've worked on some big electric motors before for running electric buses, like transit buses. And I don't know if that engineer's still alive. I'd like to send him a message.
Yeah, because I don't think I've seen a diode that big, to handle like. I'm assuming that probably puts out like kV and like a couple kV.
You know what? In that, I'm thinking. You are using something different than this in that application. You are not using a simple low side switching circuit. So there's other ways to control larger motors. I don't think it would be as simple as using a MOSFET with this is referred to, and I was saving this for another. I was going to tell you guys in another couple of minutes that this is called a low side switching circuit. And the reason for that is because the MOSFET has to be on the low side of the motor over here. So, yeah, when you're talking about a low side switching circuit, I've only ever seen it with a flyback diode.
Okay.
Yeah. Yeah, sorry I don't have any more. I wish I had some more like insight into that for you. I can always look it up. What time is it? 8:40. What else do we have? Okay, so this next part that I'm going to talk about with MOSFETs, I'm going to save this for next class because I want to give everyone a little extra time in lab today. So at this point, we're finishing up the common emitter lab. And the common emitter amplifier lab, you should already have the hand calculation and you should have the LT Spice model for it. So at this point, we're talking about breadboarding the circuit and hooking up that MIDAC. Okay, so I'm going to give everyone a little extra time in lab today to do that. Now, let me go ahead and show off a couple of things here. On the 311 page, for installing the software, I just created a page for it, walks through exactly how to install that software. And then I did an introduction video. I sent this out as an email last week. So hopefully you've had a chance to sort of look through it or peruse through it. But it walks you through how to set up the MIDAC. So if at any point you're struggling with the MIDAC or you use it one lab and then the next lab you need a refresher, the tutorial video is here for how to hook that up. Okay, so I go over function generator, oscilloscope, how to use it in this application. So given that you should have the LT Spice for the common emitter amplifier and you calculated it by hand and you have the tutorial video for how to use the MIDAC, I'm hoping that the lab goes fairly smoothly, okay? So I'll pause there and then so that's what we'll do in lab today, and we'll also do this in lab next class.